Okay, Chem 107 Lab. I'm going to talk about molecular geometry. And specifically when we talk about geometry, there are a few things we need to remember. The first thing we need to remember is that electrons repel each other. Repel each other. And because of that, we get some basic principles in what we call the valence shell electron pair repulsion theory. Electron pair repulsion theory, otherwise known as VSEPR. And all that means is that the outside electrons repel each other. So if we have an atom there and we put two lone pairs of electrons on it, the furthest they can get from each other is 180 degrees. Okay. Same goes if we put an atom there instead of lone pairs. So if we have, say, CO2, and here's the Lewis structure for CO2, there are two atoms on the central atom, okay, the two oxygens. Let me circle them. So one, two things on the central atom, and that shape we give a name, and that is just linear. Okay, pretty simple. So if there's two things on the central atom, it's linear. Now, if we put three things on the central atom, what's the furthest they can get from each other? Let's just do three lone pairs here, just so we can see what it looks like. That bond angle is 120 degrees, okay? And if we have something like nitrate, the nitrate ion, and here's nitrate. Now notice it doesn't matter if I have a single bond or a double bond. And because this is a charged species, we have to put brackets around it and indicate that charge. Notice that this forms a triangle, okay? And it forms a triangle that it all lies in one plane. So we call this trigonal planar. In other words, if we have three things forming a triangle, there's three oxygens, they will lie flat in one plane. Basically, they are in the plane of the computer screen here. Or another way to think of it is I could take a slice through this molecule and I could slice all three oxygens and the nitrogen all at the same time. That is trigonal planar. Now, if we change out one of those oxygens for a lone pair, let's see what happens. So if we have SO2, and we put a lone pair there, now this gives us a different shape because we don't see the lone pairs, but they do repel those two oxygens and kind of bend them down. So this is bent. Sorry, I forgot what I was going to say there for a second. Now those are both molecular geometries. So let me indicate that here. Those are both what we call the molecular geometries. Okay, that's the geometry of the molecule. But the electron geometry, which is this guy up here, I forgot to mention it, the molecular geometry is trigonal planar. Now, if when the molecular geometry, when there are no lone pairs on the central atom, just terminal atoms, then these two are the same, the molecular geometry and the electron geometry. Okay, now let's go to four pairs. This is where it gets a little bit more complicated. So if we have four things on the central atom, two lone pairs, Now this is going to look funny, and I'm going to explain the way I draw it in just a second. There's this wedge right here, and there's a dash, okay? The reason for that is this bond angle here is 109.5 degrees, and this shape is tetrahedral. This is electron geometry of tetrahedral. Whoa, sorry about that. Electron geometry is tetrahedral. Now to explain this molecule, this bond here and this bond here, they lie in one plane, okay? These guys are all in one plane. But the wedge, which I'll just make blue here, this blue wedge is sticking out at you a little bit, out of your computer screen, and then that orange dash, that's going back into the screen, because this is a three-dimensional object. It's very difficult to draw it on a computer or on a piece of paper, okay? So let's look at a typical tetrahedral molecule, something like methane, CH4. And when you watch the video that has all the models in it, maybe you'll kind of start to pick up on this. It is difficult to see it unless you can hold it in your hand. So this is tetrahedral. There's 4 things on the central atom, and they're all atoms. There's no lone pairs there. Okay, and again, just to reiterate, this, whoops, wrong bond, wrong color. I meant to highlight it. This dash is going back into the screen. This wedge is coming out at you, and then the other things, the hydrogen, the carbon, and this hydrogen are all on the same plane as the screen. Okay, moving on. 4 things around the central atom, but we're going to put a lone pair on here. This is ammonia, okay, and this shape is what we call trigonal pyramidal. Again, difficult to see on the screen. However, if we highlight some stuff, the electrons and the hydrogen are all in the same plane. The wedge is sticking out at you, and the dashes are going back into the screen. So you can imagine it as a little pyramid. Nitrogen, or the electrons, really would be at the top. The hydrogens are the base of the pyramid. And they're the only things, if we were to set this thing down, the nitrogen would not touch the countertop or wherever you're setting it, whatever surface you set it on. Only the hydrogens would. Okay? And then one final shape that you guys need to know, very typical molecule that we encounter every day, H2O. Okay? Again, 4 things around the central atom. 2 of them are lone pairs, 2 of them are atoms, and this shape is simply bent. And I didn't draw it in really any kind of a geometry here, but there it is. I guess I just got an email. Okay, so I guess that's it. Sorry.